Welcome to our afternoon session. We'll start with from time to space-time to no time. Please notice the question mark. The philosophy of relativity theory, which will be presented by Matt Farr. To you.
So thanks very much, and thank you for the invitation for today, and for everyone for actually coming. It's a very impressive turnout. So today I'm going to talk about the nature of time and how it's affected by our understanding of relativity theory. Now I'm pitching this as a non-technical talk, but there's as much philosophical detail as you want there to be, and I'm going to leave hopefully plenty of time for questions and to be relatively objectionable in things I say, to give you things to ask about. Good, so I travelled here today from a place called Cambridge. You might have heard of it. Yeah, I know. It's very confusing because I know the names of lots of the colleges here, but they look different and they're in the wrong place. So Cambridge, unsurprisingly, is it's a city full of bridges, and it has a river called the Cam, and this is the river, and the river flows, and it flows in front of Trinity College. This is the Wren Library at Trinity College, and if you go into the Wren Library, you'll find a copy of Newton's Principia. And Newton, in the Principia, he wrote it in Latin, but I don't read Latin, so I've translated it here. He says this thing about time. He says that absolute, true, and mathematical time of itself, from its own nature, flows equably without relation to anything external. Now, there are plenty of debates among Newton's scholars as to what he really means by time flowing. In one sense, well, he just gives a name to some feature of time you need to assume in order for his equations of motion to make sense. Other people feel that he held a very rich metaphysical view about the nature of time. And this idea of time flowing, it goes back to pre-Socratic debates. People like Heraclitus, who had this notion that time was literally like a river, that it's essential to reality, that things are constantly changing. You can't sort of freeze frame reality. Reality is like a flowing river, it's never the same at any 2 points. And in the 20th century, there's this line which goes as follows, that there's this rise of space-time physics in light of relativity theory, which changes our notion of time from something which is inherently flowing with this division between past, present, and future, to this idea of time as sort of fixed and extended in many ways like space is. So we can ask these questions, what does it mean for time to really flow, and does time really flow? And in what sense, if any, does relativity theory show us that the universe is really static, that it lacks some key element of time? So the special theory of relativity is most famously understood in terms of what's known as Minkowski spacetime, this geometrical formulation which kind of made sense of Einstein's theory. And this is Hermann Minkowski, very well dressed here, who once in a lecture in Vienna made this claim about his view of space-time. He said that henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. It's a very evocative idea that we have to update our notion of what time and what reality really is in light of this kind of new mathematical framework for relativity theory. So what I'm going to look at today, I will go through two broadly different philosophical ways of understanding time. Firstly, what I'll call dynamic time, and then what I'll call static time. Now, I'm not a big fan of the labels, but they're kind of stuck in the literature, and I'll give some ideas of why I'm not a big fan of the labels. Then I'll look at how we update our notion of time in a very non-technical sense from classical physics to relativity. And then we'll look at what it means to argue that, in some sense, time isn't real, in light of certain facts, certain key facts about relativity theory. And then, like a philosopher should, I want to reassure you with some speculation at the end, that the conclusions they're not too radical to be upset about, but radical enough for the talk to be interesting. So we can start with dynamic and static time. Right, so a couple of quotes. Here's Hermann Weyl the mathematician. Now he's talking in light, of the rise of space-time physics in the 20th century. He said that the objective world simply is. It does not happen. It's only to the gaze of my consciousness, crawling upward along the world line of my body, that a section of the world comes to life as a fleeting image in space that continually changes in time. It's this idea that really our lives are just spread out before us like a sort of four-dimensional map. And it's only from our perspective that things seem to have this animation. But there's a kind of a more objective perspective relative to which that's just all some sort of image, some illusion. Certainly Einstein seems to have held a similar view. He wrote a letter to console the family of his close friend Michel Bessot after he died, in which he said that we physicists know that the distinction between past, present and future is only a stubbornly persistent illusion, right? That the past is still out there, right? The future is out there as well, but it doesn't feel like that to us. We're stuck in this illusion that we can't rid ourselves of time as passing, of the past as gone. And various physicists, in light of 20th century space-time physics, have kind of expressed this reticence about physics seemingly leaving out some key element of reality that we have other reasons to believe in. So Arthur Eddington, another person who spent a long time in Cambridge, said that something, namely the passage of time, must be added to the geometrical conceptions comprised in Minkowski's world before it becomes a complete picture of the world as we know it. He had this idea that we have this kind of background knowledge that time really does flow, really does pass, but this isn't represented, he thinks, in the kind of four-dimensional framework in which we do relativity theory. And much more recently, the physicist Paul Davies says that this sensation of the flowing, of the passing of time, is this aspect of time of great significance that we so far overlooked in our description of the physical universe. So it's this idea that physics actively leaves out this sense of time that we seem to be acquainted with. So it's quite common to see these different pictures, these different prototype models of time. Right, on the left, it's not too helpful because dynamic time is rather static here, it's not moving, but we'll come to that. But we have this idea that there's a present moment that determines, for example, where the moon is relative to the Earth. Now we know through the laws of motion where the moon was relative to the Earth in the past and where it will be in the future, and we can draw out this kind of corkscrew image holding the Earth effectively fixed in this coordinate system. But we know that there's this fact of the matter as to where the moon is now, where the Earth is now. That's the present moment, right? And we feel like the present moment is always moving forward, changing these facts. Whereas on this other picture, we get rid of the present moment, and we just have this static block with all these facts about the motion of the moon relative to the Earth over time. So on the first view, the dynamic view, we have this idea that time is quintessentially carved up into these dynamic regions of past, present, and future, that the present is the key thing where we feel like we are, which is always changing. It takes us towards the future. And we can think of the present as some sort of three-dimensional manifold of events, and all of those events in the present are simultaneous, they're all happening at the same time. Whereas on the static block, we picture time as part of this four-dimensional universe, whereas time doesn't have some quintessential property that is lacked by space that makes it special in the same way. On this picture, we don't have objective regions of past, present, and future. It's just that relative to some point, you might distinguish between the past and future, but that's just because of where you are. Like other people in the past will think that you're in the future, and so on. And you're not right and they're not right. You're disagreeing over a matter of perspective. On this view, events don't really come into being. There's no kind of process of temporal passage on this view. And if we think about reality being like this, there's no real need for us to hang on this idea of a global simultaneity relation, of a global now that kind of slowly builds up reality. And that becomes quite important when we think about a key feature of special theory of relativity. So going back to this idea of leaving something out, This is a common attitude taken towards the block universe or the static depiction of time. The very usage of the term static implies that it could be moving, but it's not. So it's common to hold that this view of time, this four-dimensionalist view of space-time, leaves out something essential, or it somehow spatializes time. But it's important to focus on what this really means. In one sense, the term static doesn't make a lot of sense. When we think about something being static, we think about it staying in the same position over time. Right? But the four-dimensional universe doesn't stay in the same position over time. It is time, right? Some people have suggested, well, maybe we need a second-order time and that it's static relative to that, but there's no particular reason why we want to invoke such an idea. There's a sense in which it's not something which could be moving, it's rather a four-dimensionalist way of representing motion. And it's quite important to think about the distinctions between kind of the properties of something which is being used to represent things and the things that it's meant to be representing. And this is something which is very common within physics. I mean, very simply, I could say that this is a two-dimensional representation of a three-dimensional cube. You can think that in my, putting this on paper today, what I'm doing is trying to connote the idea of depth in the third dimension. This really is my way of representing something in three-dimensional space, even though you're seeing it on a two-dimensional surface. Is it not similar to represent the flow or dynamism of time using this sort of fixed block? So there's an interesting sense in which the notion of static is already quite problematic. Maybe it's okay to represent a kind of a world with the various whoosh and whiz of our temporal experience, even though it's represented in this four-dimensionalist way. So dynamic and static time, they crop up a lot in the literature with various different names. You might be familiar with the idea of the A theory and the B theory of time, which really latch on to the same ideas. They go back to this very flatteringly depicted metaphysician here, John McTaggart Ellis McTaggart, whose name appears twice there. There's two McTaggarts because he was initially called John McTaggart Ellis, but then there was some legal issue where he only stood to inherit a large fortune if his surname was McTaggart. So he was a very clever metaphysician. So he had this language of the A series and the B series. He thought there's different ways which we ordinarily talk about time. Sometimes you talk about time in terms of whether something is past, present, and future. For example, this conference was future. Now it's present, it will be past. So if we want to order things in terms of an A series, we have to keep redrawing the A series. For McTaggart, that's kind of how we represent the flow of time. It's these facts that change that constitute the flow of time. But we also have this other way of talking about things. So Alistair Wilson's many talks today were all earlier than mine. And that's a fact that kind of is always the case, right? Time doesn't pass in terms of the changing of these earlier than relations. They're kind of, in a sense, always fixed. So in that sense, McTaggart thought that this B theory is static. It's static because the facts that build it up, the relations that build it up, aren't subject to change in the same way as something being past, present, and future. And another relevant distinction here, which again is very closely related, is between what's known as presentism and eternalism. So presentism effectively kind of gets rid of all the past and future stuff. It's this idea that reality is just constituted by what's going on right now, right? The past isn't real, the future isn't real. Certainly there are facts about the past. We have records in the present which seem to necessitate certain facts about the past. Likewise, we can make predictions, very reliable predictions about the future. But we don't think that these things are set in stone. They're not really out there in the same way that the present is. We can think of the past and future as sort of abstractions based on knowledge that we gain in the present and memories that we have, again, in the present. Whereas eternalism is this idea that the past, present, and future are all, in terms of their ontology, in terms of their existence, they're on a par. They're equally real. Right? The past is no less real than the present, and that's what Einstein was really getting at when he was trying to console the family of his friend. So present things certainly seem special to our perspective, but that's true for people located anywhere in the space-time block, because they'll take their time to be present. But the main idea here is that the future and past, they are somewhere, they're really out there, right? They're as physically real as what's going on around here in Oxford today. So they're the main kind of different philosophical views of time that I want you to have in mind. And then we're going to look at how these are affected by our understanding of relativity theory. So in Newtonian spacetime, we have this key notion of absolute simultaneity, and it's kind of given to us by the fact that space and time have different metrics for Newton. So we can think about three happenings, call them A, B, and C, and say, well, they're at the same time if they are simultaneous. And then we can think of all the things that are simultaneous with each other and say, well, that's a moment of time. Right? So A, B, and C are simultaneous, but at a later moment of time, none of these first events are simultaneous with any of these later events. And we have the universe being built up in this kind of nice temporal way. Now, as time passes, right, we can think that ultimately we can build up this entire universe of just stacks of present moments, stacks of nows. And we can add all sorts of properties to them. Like I said, you can think of them as having a present moment which moves up, or you can think of them in a sort of presentist way and just have this particular moment which is always sort of moving upwards. Now, this picture we get from classical physics is troubled by kind of the very central idea in relativity theory, which comes out of Einstein, one of Einstein's famous 1905 papers. I don't speak German very well, even though I lived there for a few years, so I'll just translate that. This paper on the electrodynamics of moving bodies, and it's called this because he's trying to fit together certain features of Maxwell's electrodynamics and Galilean relativity, the physics of moving bodies. These give rise to these two central principles in the theory, which he introduces in the paper. So he uses the terms the principle of relativity and the principle of the constancy of the velocity of light, but these days it's usually simplified to just the light postulate. It's a bit easier to say, and it's kind of a fairly simple principle. Now, these two principles are as follows. The relativity principle, effectively, it's what's taken from Galileo. It's what Galileo famously appealed to explain why we don't feel the Earth's motion around the sun, right? If you have something in some sort of continuous motion, as in uniform motion, it will undergo the same forces as something at rest. So if you're uniform motion with respect to the Earth, you're not feeling any particular forces. The physics in your uniform motion will be the same as if you're at rest with respect to the Earth. And the light postulate is the idea that the speed of light in a vacuum is a constant. It's always going to be measured to be the same, which we use the term c for this. And that comes out of Maxwell's equations. Einstein was interested in how you can fit these two things together, hence the title of his paper on the electrodynamics of moving bodies. And the problem is quite simple to show as follows. So imagine you have this very simple depiction, a very simple experiment. You have a light bulb, you want to turn it on, and you want to mark when the light beams hit the left wall and when they hit the right wall. So you turn it on and you fill in the details as follows. So we know the speed of light in the vacuum, and we say we have the same distance to the two walls. Given that, then we should have the same time taken for the beams to reach each wall. You can plug in numbers here. It's not particularly important. I did this for completeness once, but you can kind of gloss over that. Just to say light is very fast. So don't try to do this experiment unless you have a very big lab. And the question that Einstein was interested in is what happens when you have this lab moving. And this is where you get this kind of interesting thing about simultaneity. So we have to have two frames, right? Someone's going to be on board the train, kind of not moving with respect to the experiment, and someone's going to be on a platform and moving with respect to the experiment. So physicists always talk about Alice and Bob as the two experimenters. So we'll bring in Alice here, and her job is to turn the light bulb on and get the original measurements, right? Which, given Galilean relativity, that's going to be a triviality, right? This is a fact about the world, right? If we have a uniformly moving train, I mean, it has to be very, very uniform, but you'll get the same results as in the original case. The interesting situation is what happens when we bring in the second observer. Right? This all follows from Galilean relativity. But when we bring in a second person, Bob, this is already a very outdated reference, I have to say. I was quite shocked to see that they've got a new Bob the Builder now that my daughter watches, and he doesn't have any of the qualities of the original Bob. It's very sad. It makes me feel very old. So Bob here, it's suddenly not straightforward what he's going to measure. Right? So let's suppose we assume absolute simultaneity, that there is this thing, this kind of present moment, that if two things are simultaneous for one person, they're simultaneous for everyone. If we assume that, then we don't manage to preserve the light postulate. Why? Well, we know that this thing is moving relative to Bob, so the front of the train is moving away from the source of the light, the back of the train is moving towards it, so the light has to travel kind of a greater distance to the right wall than it does towards the left wall. If these two events are to happen at the same time, that means that light can't be travelling at the same speed in the two directions. Right? It's kind of not particularly complicated mathematics to figure that one out. This saves us this notion of absolute simultaneity. If two things are simultaneous for Alice, they're simultaneous from Bob, but it gives up the light postulate because it says that the two velocities taken here are not the same, and given that this is light in a vacuum, they have to be the same, otherwise we've violated the light postulate. So what Einstein says that we do ultimately is to give up this notion of absolute simultaneity. Right? Instead, we just assume that the light travels at the same speed in both directions. And in order for that to be the case, we get something more like this. And it's a highly idealized illustration of the situation, but it's to give a kind of an intuitive idea of what's going on. So what's happening here is that in order for the light to be traveling at the same speed, we have the two events not happening at the same time. Right? The left event is happening before the right event. Now that seems kind of fairly straightforward here, but it has a fairly significant philosophical consequence, which is that two events which were simultaneous for one observer are not simultaneous for another observer. Now if we think that the world is built out of slices of simultaneity, out of global nows, then this seems to be contradicting that in a very basic sense. Right? And this is why various philosophers and physicists have been troubled by what relativity says about time. Right? To preserve this frame independence of light speed, we have to give up the very idea of the two events having some universal, objective, invariant order in time. Right? For one observer, they can be simultaneous. For another, one can be before the other. And for another observer, the order could be flipped. So to kind of just see all the different situations that are going on here. Now what we learn from relativity theory is to try to understand this apparent discrepancy in terms of a unified framework. And what we give up is the very idea that there are facts about whether two distant events are really happening at the same time. So this notion of absolute simultaneity, it plays a central role in Newtonian physics, but it doesn't play a central role in relativistic physics. It's something that we have to kind of give up. And this is what was built into this mathematical depiction of reality that Minkowski gives. So Minkowski, famously saying that we only have this kind of union of space and time having this continued existence, he introduces this notion of a light cone as the kind of central geometrical idea in his picture. The light cone is because everyone is going to measure the speed of light to be the same. So we see here that this is kind of effectively a beam of light going towards the future and spreading out, and likewise all the possible light waves that can come in from the past to a certain point. And he says that what we have is this metric, the Minkowski metric, which you can plug in your particular results for how far things are apart in space and in time, and what you get is this ds squared thing, the interval, the space-time interval, and that's what's objective. Now, the interval can be time-like, and that's just in case that you have two events where one is in what's called the future light cone of the other. You can get from here to here whilst travelling slower than the speed of light. You can have a space-like interval where two events are so far apart that light can't travel between them. You can't send a signal between the two. And you can have a null or light-like interval where only things travelling at the speed of light can get from one to the other. So the idea in Minkowski spacetime is that we have this objective time order for things which are time-like separated, but things which are arbitrarily far apart and are space-like separated, there's not going to be an invariant ordering of these things. So the philosopher Hilary Putnam wrote a paper some years later than Einstein-Minkowski's work, where he raised problems for the very idea of how to think about reality as ordered by time. So imagine, again, we have these observers, Alice and Bob, and there's a particular time at which they pass each other in the corridor travelling at different speeds. We can imagine two space-like separated events, with it being the case that the different coordinate systems relative to which Alice and Bob are at rest will disagree as to the time order of these two events. And Putnam says, well, imagine we want to say something like something is real only if it's in the past or in the present, like only things which have happened are real. We have the problem that for Alice, at this particular event where they're meeting, this event Q is real because it's in the past, but R is not. And for Bob, we have R being real and Q not being real, meaning that we can't have these kind of independent ways of slicing up reality in terms of these global nows that then accord to this idea that the past is fixed and the future is open. Putnam was really troubled by this. He said that the main takeaway is that we don't really think reality is relative in this way. Right? Reality is not relative to each observer. If something's real for me, it should be real for you. If it's real for me, it should just be real. Now, there's a couple of different ways that people have tried to save this. So there's this particular approach that some people have taken to effectively give up the Einstein-Minkowski reading of relativity theory and go back to an earlier view, which was associated with Hendrik Lorentz. Lorentz said that his notion of time is so definite that he clearly distinguishes on his picture what is simultaneous from what is not. So how Lorentz understood the different coordinate systems that we've been talking about is that they're related by these Lorentz transformations, but what the transformations tell us is how different people's measuring instruments are affected by motion through an ether. On this view, we could imagine that maybe Alice is right in her results and Bob is wrong, because Bob's measurements, his meter stick and his clock, are affected by the motion through the ether in a particular way, which Alice's are not. There are various people that have tried to save the idea of time being dynamic by appealing to this notion that we just don't adopt this newer view of relativity theory. The trouble with this is that it seems to be giving up a development in physics on grounds of preferred metaphysics. Right? So you might be able to get an absolute temporal ordering for events out of such a picture. You might have a global now, but it's something which the various symmetries of relativity theory tell us is going to be unobservable. Right? So this, in a sense, supports the notion that time passes as a sort of global phenomenon, but it has various unnaturalistic aspects to it. It reverts to this abandoned scientific idea on the grounds of preferred metaphysics. I'll go through one more thing and then I'll head on to the conclusion. So an alternative approach, which is associated with the philosopher Howard Stein, is to say, well, we can still have a distinction between past and future in terms of what's locally past and future. Your past light cone determines all the things that have happened relative to that point, and the future light cone the things that haven't happened. Can we build the notion of the passage of time in terms of this? And the philosopher Craig Callender, I think, hits on the main problem with this general type of approach. What it's trying to do is to say that there's no real global extent of the present moment. The present moment is like a point. But he says that any notion of temporal becoming, of the passage of time, remotely similar to that which is initially advocated by by philosophers prior to relativity doesn't really seem to be fitting with this idea. The problem is that we seem to have lost some of the key intuitions behind the picture of dynamic time. Right, on this view, there's no universal background time which is ticking along. Time is going to pass, in a sense, only along local timelines. There can be infinitely many passages of time, but no global tide of becoming. And the question is whether this kind of time is really worth saving. Okay, I think I'm going to skip to the reassuring speculation since we're about that time. Yeah, speaking about the passage of time, I'm not a fan of the passage of time because it's always a bit too fast to say all the interesting things that I would otherwise like to say, but that's why I'll let lots of questions. Okay, so just to sum up some of the key points. So special relativity entails, in a key sense, that there's no such thing as absolute simultaneity. Now, I kind of skipped over an interesting thing about general relativity, but feel free to ask me about that. Now, this implies that reality doesn't seem to be carved up into an absolute past, present, future distinction. It suggests that the passage of time, therefore, is not an objective feature of reality. There are some potential ways to kind of regain this old idea of time globally passing or even locally passing, but they have various kind of problems that seem to detach them from their original intuitions. But I wanted to end with the question of why we should worry about such things. And I think that there's this, what I call a fallacy of competition between different views of time. Right? So in one sense, we have physical time, which is time as it appears in our fundamental physical theories. It's a job for us to interpret this in a unified way, but we can do that in certain cases, like with relativity theory. Then we have experience time. And there's all sorts of features of our experience of time, like seeing motion, seeing change, and having certain kind of dynamic type feelings about that. And then there's a thing I'll call folk time, which is the ways in which we tend to talk about time, to describe time. The way we use metaphors like rivers and flow to refer to time, which are loosely based on experience. And there are some things to say here. So fundamental physics is certainly consistent with all sorts of complexities of the macro world. It's not any surprise to anyone that's done philosophy of science to see that when, if physics doesn't talk about chairs and tables, it doesn't mean that chairs and tables don't exist. With experience, there's a certain sense in which we don't directly experience something which we can call the passage of time, but we create this idea of the passage of time from our experience of things like the motion of a ball or a bird moving past you, and we can kind of turn these into metaphors to describe time, but we're not actively describing something which we directly experience. And when it comes to folk theories of time, there's senses in which folk theories are useful and sometimes unuseful, but it's often a mistake to think that they're literally meant to be true or false. When I talk about time as flowing, you get this idea. Time seems to have flowed faster during this talk than I might have liked it to. It doesn't mean that I think that time is literally like a river. When we think about things like the flow of time or a global now or the open future, it's often very hard to work out where these things are meant to be. And it's only by trying to force on us a single notion of objective time that we seem to create these paradoxes where maybe there's a lot more compatibility if we really look for it. And that's where I'll end.
Okay, thank you very much, Matt. We have some time for questions. It's been a bit contracted, but we still have it. So please, if you have any questions, please raise your hand. Yes, the gentleman over there.
I was really interested in what you said about the flow of time, because one of the key things I do is go down to the beach and look at the ebb and flow of the water. So are we both moving at the same time, or am I static and just watching the water flowing?
Thank you. Sorry, could you repeat the last thing you said? I didn't quite catch. So when you're seeing the sea,
Yeah, so when I'm seeing the flow, the ebb and flow of the beach, which is absolutely wonderful and sounds wonderful, and I'm sitting on the beach, are we both moving together, or am I static, just watching the water flowing?
Yeah. So that's a good question. So I mean, I think when we talk about the flow of time, I mean, the view that I try to advocate is that we can talk about time as though it flows. But at best, it has a kind of a metaphorical, kind of non-factual nature. Now, we can see certain commonalities with seeing the sea, the tides come in and out, and thinking about time. And very often, philosophers and scientists, they talk about, when they talk about what it means for time to flow, they come up with examples like flowing water and like moving objects. And I mean, my take on this is that the reason why these things connect to the idea of time is because we just use them as metaphors for time, but it's not a sense in which we're seeing time flow by seeing the water flow. If time really does flow, it flows just as much when we're sitting around in a static room, but we don't have the same sense of the flow of time in those cases. I think the very fact that we can kind of use these particular metaphors for flowing time is not an indication that we have any better experience of time flowing in those cases. We just have, a greater sense of this notion of transience, which can come to us through thinking about the past and reflecting on things like that. This is, what motivated Heraclitus initially to think about time as like a river, because in a river, effectively, things are always changing and things are lost, and you can't get back the same state that you had. And it's kind of reflecting much more kind of an emotional attitude towards existence than anything else.
Yes, there's somebody in the back. Question?
Hi, thanks. So I'm thinking, does the fact that the experience of duration requires time mean that the the static universe view is got to be false? Because obviously we have an experience of duration, so obviously time as a sort of separate dimension of being exists, to me anyway.
So because we have this, when you say duration, do you mean like a temporal extent or a sort of...
All experience must have a temporal extent by definition, right? So therefore time must be built into from the very fact of experience, time must exist.
Yeah, I mean, I'm certainly happy with the idea that time exists. I mean, really a key aspect of the sort of dialectic you see in these sorts of arguments is that because time is represented as more space-like, as more spatial in relativity theory, that suggests that time is somehow unreal. But you still have, even in the Minkowski metric, you have a different sign for time than the other dimensions. There's a certain way in which the physics is different for a long time than a long space. In terms of experience happening a long time, I mean, that can be related to all sorts of things, like the fact that we have cause and effect happening across the temporal dimension and not across the spatial dimension, and so on. We think about like the second law of thermodynamics. We have records of the past, we don't have records of the future, and so on. These are the sorts of things that seem to support this idea of constructing timelines, of having the sense that we are temporally extended, and so on. But none of those necessarily require us to add this idea that time really does flow or pass in the sort of picture that dynamic time tries to put forward. So one of the ideas is that there's enough richness in the static time picture to kind of make sense of our various experiences that we do have.
Thank you. I've got a quick question on the interaction between quantum mechanics and relativity.
Sure.
And that's on quantum entangled pairs, where you'll have a pair which is...
Yeah.
And they're created in upstate and downstate. I've got but they're not fixed until observed.
Yeah.
And what we're told is that one is observed and it's seen to be in the upstate. The other one is instantaneously, however far it is away, in the downstate. and this happens faster than the speed of light. And this seems to me to be inherently wrong. I was wondering what you thought on this.
Yeah, I mean, so one way it's been put by the quantum physicist Abner Shimoni is that you still have this kind of peaceful coexistence between relativity and quantum entanglement. Because what happens, so you're describing a sort of like a bell pair of particles, that they're prepared in some particular entangled state, meaning that a spin measurement, say, on one particle will determine what the outcome of another spin measurement on the other particle will be if it's measured in the same axis. What's interesting about that is that it falls short of a violation of kind of causal locality, because you have something like this, the no signaling theorem. You can't, like quantum correlations, non-local correlations are not strong enough to encode signals to send from one wing of the experiment to the other. And so one thought is that, well, you can preserve relativity by holding that relativity is talking about kind of causal locality. But there is an interesting thing where there seems to be a sense in which the best state that we can ascribe to these two particles involves this sort of holistic kind of nature, that this state really spreads out across space. It's not, you can't carve space up in terms of local regions in light of quantum mechanics. But you are unable to violate this kind of sense of causal locality. So it's a really interesting case. I mean, some people have tried to make sense of the kind of the causal structure of these particles by even introducing things like retrocausality, where my choice of how to measure this particle sends effectively a signal locally but backwards in time to the original state of the particle. So there's all sorts of possible ways which we can try to interpret the causal relationship between these non-local entangled particles. But there's no direct contradiction with relativity theory in that sense.
Thank you very much. I think that's it for questions.